First of all, I am aware that this is the second presentation of reactive programming, but as you will see, it complements the other presentation because it's mostly on reactive programming in general, so the high-level overview, and then slide into the Java ecosystem, and then a little bit in Spring. So hopefully it will not have a lot of overlap with the other presentation. So that's what I wanted to clarify from the beginning. Just a second. Hopefully. Yeah, for some reason the pointer isn't moving to the next slide, so I'll switch it manually. This is the agenda. First and foremost, I will do a short high-level presentation because it's usually introduced in my slides. Then a reference frame. Just a second. No. Afterwards, we will do a short reference frame, so to place the presentation in the services architecture and microservices architecture, and to understand the components communication, then an overview of reactive programming, then an overview of reactive systems, manifesto, and streams. So basically a lot of reactive entities and concepts. Then the reactive model, main reactive libraries, and the Spring reactive programming support, but that will be the last part and just a little bit. So mostly it will be a high-level overview. Briefly, I'm working as a trainer and consultant and coach at my own company. Approximately 11 years of experience in design, development, architecture, so end-to-end pretty much, and the last 2.5 years I've spent as a trainer and mentor and coach. So this is mostly what I've done. I have two requests. Please ask questions, and the second one, ask questions. So, and please put your phones on silent. If you have anything, please go outside. So we don't want to be just all of a sudden interrupted by some important call. As a high-level overview and a reference frame of the services architecture and microservices, so as you see the micro in there, it's slightly dimmed. Usually from an internet endpoint through an UI or through an API, we are accessing an enterprise system. That enterprise system usually has on the configuration layer several components which are facilitating the communication, the external communication. In the business layer, usually we have several services which are communicating between themselves. And those services might communicate or will communicate either synchronously or asynchronously, perhaps using some message brokers or accessing some big data, or perhaps persisting their data to the database. So this is the high-level overview of where the reactive programming will come into place. We will speak later on more in detail about the reasoning, so the why and the how. A high-level overview of reactive programming. I'm an adept of less is more, so I'll try to keep it short. First of all, it's a programming model which is built around reacting to change. So the reactive part from reactive programming refers to the reacting to change. Changes might be in several modes, but especially the possibility for one of those services to process a certain event or a certain message. Also the availability and processability of events or messages, but basically around reacting to change. The main benefits of reactive programming, so why would we want to use reactive programming? It is completely non-blocking and asynchronous. So two benefits, like two in one, but those come with some challenges and some, not necessarily prices, but with some challenges, as we will see. Also, they provide, so the reactive programming paradigm offers an improved or optimal hardware utilization. So by using reactive programming, we are using the hardware resources in a much better, towards optimal way. The challenge is, first and foremost, the reactive code base cannot coexist with a blocking code base, especially, that is a challenge, especially in the JDBC and the servlet API-driven applications. Also, no blocking SQL access is still in development. As the previous presenter has mentioned, there are several asynchronous or reactive JDBC drivers, but reactive database access, reactive SQL database access is still in the beginning. If there is any short question in your minds, reactive JPA, no. A few augmenting or complementing definitions, set of design principles for systems architecture, style of microarchitecture, and a programming model that facilitates scalability and stability. We will see a little bit about those as well, a little bit further on. A few clarifications on the reactive programming and derived concepts, meaning systems, streams, and manifesto. The reactive programming term refers to the programming model used for creating reactive systems. Those reactive systems are what's the end result, meaning architecture which are designed to be reactive to change. Meaning it's not enough for just one application to be reactive to changes and to events, but we need to have the entire system be reactive so that we have an entire reactive system. Streams, the reactive streams, it is a standard for asynchronous stream processing. It was established through a collaboration between several big players in the Java ecosystem. Netflix, Pivotal, Red Hat, Twitter, and some others, TypeSafe as well. The Reactive Manifesto, it was an initiative to standardize and unify the characteristics of reactive systems. We will see an overview of the main characteristics which are included in that manifesto. A short history. First of all, the reactive programming term or the concepts of reactive programming are not by any means new. They were initially developed around 1970, which is a lot of time, which means approximately 50 years. We will answer the question, what took it so long? The Reactive Manifesto and Reactive Systems concepts appeared around 2012, the Reactive Streams around 2015, and the inclusion of the reactive support in Spring 5 in 2017. Short overview of the Reactive Manifesto systems and streams. The Reactive Manifesto summarizes a few architectural patterns for building software that is robust, resilient, flexible, and of course better positioned to meet modern demands, which is a lot of data. It is highlighting the main characteristics of reactive systems, meaning responsive, elastic, message-driven, resilient. And the manifesto was the basis for the reactive streams. As we will see soon, the reactive streams was the, let's say, the API on which the reactive libraries have been developed. A few use cases and the answer to why now, because you might wonder what took it 50 years. First of all, the use cases, especially for HTTP service calls, meaning either internally in an application, when an application communicates with several other internal services or microservices, or external when the services are performed towards other parties. Highly concurrent message consumers and abstractions over other synchronous or asynchronous processing layers. And why now? Because, first of all, the technology has evolved, both hardware and software. The rise of microservices and the rise of multi-core processors enabled the development of the reactive paradigm, the reactive programming paradigm, and the data producing and processing requirements. That's one of the key factors which have driven the development of the reactive programming ecosystem, because it is ever increased. More data is produced, more data is processed, and especially the end users always want results fast. They want them like that. So if it's possible, yesterday to have them, or a few minutes ago. Just the a short overview of reactive applications, so applications which are reactive to change and use reactive programming for their business. And those reactive systems, as previously mentioned, are systems composed from several reactive applications. They are or should be designed to coalesce as a single unit. So react to the surroundings and to the events which are happening in that system. And of course, the most important question is how do we build those reactive systems? The short answer, it's complicated. I mean, it's not that straightforward. And the other answer, it might be the, I hope you know the most common answer from our domain. I presume from some other domains. Do you know? Exactly, it depends. It always depends. Thank you. High-level overview, bless you. High-level overview of the benefits provided by the reactive systems. First and foremost, I want to highlight the summary. Those reactive systems are the most productive systems architecture that we know of. That's a pretty bold statement, and that refers in the context of multi-core cloud and especially multi-core and cloud applications. So they are the most efficient and productive. They provide isolation of failures, message passing, location transparency, replication, and elasticity. Of course, a lot of these details are not explicitly linked to the reactive systems, but are also architectural patterns and especially enterprise patterns. But they are further improved, or they are further enhanced by the usage of reactive systems. We will soon see a comparison. A use case, an interesting use case, one service which serves around 100 million users. It combined the effects of the benefits of reactive programming and microservices, and it led to less hardware resources, less developers needed, quicker turnaround, and more traffic with cheaper operations. So that system handled more load on 13 servers than another similar system on 2,000 servers. That's a huge difference. And also needed a very costly DevOps team, perhaps our colleagues from nearby, to monitor and tweak that application. And another company in the same industry had 150 servers. So perhaps not the same requirements or the same specifications. As a high-level overview, a difference between the classical and the classical meaning thread per request and the reactive systems which are using an event loop model. In the classical thread per request model, which you might know, hopefully you know, there might be a load balancing layer on top of the application. There are several instances of that application. That application has at its entry point high count thread pool, usually from a web server or an application server, has a presentation layer, business logic layer, data access, and beneath that data access layer, it has a blocking JDBC driver. And it accesses a SQL or NoSQL database, and it is usually encapsulated in a servlet-based container, which is by its nature, by its code, which is blocking. The alternative, or the event loop model, uses a low count thread pool, which is usually sized according to the number of cores from that server, from the running server. On the presentation layer, there are several subscribers exposed. The business logic layer just takes those requests and communicates with a publisher from the data access layer, and that publisher communicates with the database, either SQL or NoSQL, through a non-blocking either JDBC or NoSQL driver. And everything is served through an event loop-based container. So we will see more in depth about these details, but this is a high-level overview of the different model. So end-to-end different model. A few more details per layer. So that consumer, either an API or an UI, will access a server or an application through a log count thread pool, through the presentation layer, or the presentation layer, several subscribers, as previously mentioned. Data access layer contains several publishers, and then the drivers will communicate with a NoSQL or SQL database or with some external systems. But everything is first and foremost based on an event loop model. We will soon see what that means. And it will use non-blocking and asynchronous calls. So nothing blocks, ever. Or at least ideally, it won't block. The event loop request processing model entails several phases. First of all, clients are submitting requests. Those requests are interpreted as events. So someone asks for the product. Then those events are delegated to some event handlers or workers, which are performing that business logic. Then those handlers or workers will respond via callbacks. And those callbacks will further return the response. And everything is backed by an event queue. The key point, this event loop model is using a single thread. So non-blocking, hopefully that will disappear. And it is using internally a circular ring buffer queue. So everything is non-blocking, and it's a circular ring buffer so that all the events are not blocking while they are in that queue. In a glance, the differences between them: on the blocking model, so the usual and traditional thread per request, each request is handled by a pool thread. That means we need large thread pools, especially when there is a high load on that application. It's usually based on the servlet API, which is at its current version, it's version 4. Starting from 3.1, it contains a non-blocking component, but still some internal components are still partially blocking. No blocking I/O, sorry, just non-blocking I/O. And the main web containers for the servlet stack are Tomcat, Jetty, and Undertow, especially in the Spring and Spring Boot ecosystem, because that's what we are speaking about. On the non-blocking model, as previously mentioned, the application will use an event loop model. That event loop, as we've seen in the previous slide, will use several worker threads for that processing, uses smaller thread pools, which is a very important difference. And as a stack, it uses the Reactive Streams libraries, which we will soon see. And the main web container is Netty. So that's a new hipster web server in the Java ecosystem, which is called Netty. Hipster in terms it's younger. It's not using the traditional thread per request. It is more lightweight, more thin, on the less is more paradigm. So reactive, async, parallel, and non-blocking. A lot of goodies. The enablers of the reactive programming, I have divided them. Was there any question? Any objection? Anything? Okay. So the enablers per application parts, components. On the front end, we can use HTTP2 to enable requests multiplexing, which will lead to faster page loads. If the internet would work, we would see a demo for that, but as far as I've tried, it's not working yet. There is the counterpart of the reactive libraries from the backend on the front end, which is Rxjs, Reactive JavaScript Applications. So the front end already has reactive support. The backend, as previously mentioned, in terms of web servers, we have the reactive-enabled server, the main one for now, Netty. On the presentation layer, usually the controllers are returning reactive endpoints. Service layer, we have several subscribers and several reactive pipelines. We will briefly discuss about them. And on the data access layer, we are returning data as reactive publishers. So this is the high-level overview and the main ingredients of having an end-to-end reactive stack. Brief overview of reactive streams, and then we will see the implementations for the reactive streams. The reactive streams appeared as an initiative to provide a standard for asynchronous stream processing with non-blocking back pressure. That back pressure we will briefly describe a little bit later on. Basically refers to the subscriber telling the publisher not that fast. Please back away and deliver messages or events in a slower mode. So that was the summary. The destination tells the source how much data it can handle through that reactive API contract, which we will soon see. We will also see that in that publisher and publish-subscribe model, the subscriber requests several items from a publisher, and the publisher will push those items. So it's not the traditional pushing mode, which is usually used in traditional applications, which when the API or the UI will just push some data. This is a nice overview, I think. Publisher is the speaker, subscriber is the listener, just listen to things. And we will see there is a contract between them. But before going there, high-level overview of the Reactive Streams API components. There are just 4 libraries: publisher, subscriber, subscription, and processor. Publishers are the data producers, subscribers are the data consumers, briefly, and the subscription is the contract between them. So we will see more details about these interfaces in the next couple of slides. They were included in the JDK since version 9 as the Flow API. There are a lot of details on their usage, a lot of details on those contracts. But basically, those 3 interfaces are those that are used in the reactive programming model, especially using the Spring Webflux component, which we'll get to very soon. So, besides the publisher and the subscribers, we have subscriptions. So those subscriptions are the interfaces through which a subscriber can tell a publisher, please slow down. Please send more messages in a slower rate. So that's the back pressure which we referred to earlier. Libraries. Several libraries in the, please. Yes, through these interfaces, especially through the subscription interface and through the methods from the subscriber and the publisher, there is a way through which those subscribers, because a publisher can have several subscribers, those subscribers can automatically send messages or tell the publisher to slow down the producing of the messages. If we would want to go more in depth, we would have to get to the code and see those details. But basically, it refers to several interfaces with several implementations. And when we'll get to the implementation, perhaps we will see a few of those details. As a high-level overview, it refers to some method calls between those 3 interfaces. Sorry. I'll clarify also the bridge or the link between these interfaces and their implementations, because of course we need to have implementations. The main reactive programming libraries, Rxjs, which was the first reactive programming library, Akka Streams, Project Reactor, Ratpack, and Vertex, first of all. These are the main, at least. They all implement the Reactive Streams API. So they all are implementing publishers and subscribers. You can think of this Reactive Streams API as the JPA, because JPA is just an API which has several implementations. We can think about the Reactive Streams API in the same way. A high-level overview of Project Reactor, so which is one of the main and the most used libraries. We don't have enough time to speak about its history, but it stands at the core of the Spring Web Flux component, which is the reactive programming part from Spring 5. And it implements two main modules or libraries, Reactive Streams API and Reactive Extensions. By implementing those reactive extensions, it makes it compatible, especially with ReactiveX and with Rxjs. So that bridges the contracts between them. The Project Reactor has two main publishers, which is a mono and the Flux. The mono is a publisher of 0 or 1 items, so it's not sending a lot. And the Flux is a publisher of 0 to 1 items, potentially unbounded. That's the good part. So we don't have any guarantee whenever we have a Flux publisher that stream of data is finite. So it might be infinite. And now we get to the Spring Web Flux part. So everything till now was an introduction of what is reactive programming, what are the components, and then zoom into the Spring Web Flux. In brief, the reactive programming part or component from Spring version 5. It was introduced or launched in Spring 5, which was launched in September 2017. So it's still, we could say, young. A foundation for completely asynchronous processing using non-blocking I/O, meaning a complete new way to deal with requests and responses. That means it is no longer based on the servlet API. New classes, new non-blocking contracts between them. So we no longer have the HTTP servlet request, HTTP servlet response, and all the other session and so on, because they were blocking internally. And we can see it in brief as a reactive version of Spring MVC and REST, I would say, especially on the REST part. A high-level overview of the WebFlux API stack. It's at its core, so there is the Spring WebFlux core, a set of new libraries and classes and interfaces. The Spring Web API contains two main libraries, the Project Reactor library and the Reactive Stream specification. So both the interface, the set of interfaces and the set of implementations. It can use both the servlet container, so servlet container web servers or non-servlet container web servers. Those servlet containers, as we've seen, we have spoken, are mainly thread per request model web servers, Tomcat, Jetty, and Undertow being the main web servers at least. I haven't spoken anything about application servers. You might know those huge monsters. Usually their names start with WNS, WebSphere, what's the other, WebLogic, WebSphere or WebLogic or something. So they can also be used, but usually in the microservices world, they don't really fit in. So that's why I'm referring mainly to Tomcat, Jetty, and Undertow. And on the non-servlet container world, for now, there's that web server called Netty, which is using an event loop processing model. So this is as a high-level overview of the WebFlux API stack. A brief overview of Spring MVC versus Spring WebFlux. The Spring MVC, we can include there definitely the Spring REST support as well. Uses the servlet API using a blocking I/O, and it uses Tomcat or Jetty or Undertow as the web server. The Spring WebFlux it is using the Spring Web API, using Project Reactor and Reactive Streams. non-blocking I/O, especially to netty. So that non-blocking I/O, it refers to netty. The other one, it can be also used, but then it will block on the web server part. These are two extremely simple examples, and pretty soon I will have, it seems, enough time to get to the code as well, so to open my IDE and to see some code. In brief, those two publishers which we discussed, which we've mentioned so far, meaning the Mono and the Flux, can be exposed via REST endpoints, so that whoever invokes those endpoints, meaning the Mono and the Flux in these examples, will get back either a Mono or a Flux for those for that type, for a product in my example. And in this example, I haven't included any other component, meaning the business logic or data access, but the entire application can be seen as instead of these. So instead of returning the end component, it can go through all the layers, meaning the presentation, the business logic, the data access, and so on. And then the SQL or non-SQL database. Before going there, let me get a little bit to the component. I'll also open. Okay. Let's put it on presentation mode. So, in brief, these are a few endpoints exposed through a REST controller. I hope everyone is familiar with the Spring Web annotations and Spring Web terms. If we will want to see further details for the reactive processing chains which are available from each of these, we can further see how we can create monos, for example. In this extremely example, I have just created a mono from something simple, but we can use create, we can use the bridge towards a callable, so everything which returns a callable, meaning future implementing or future returning classes, or the bridge to the completable future API from Java 8, or from runnable, supplier, or a lot of other. And from there on, after using one, we can zip them, we can delay them, we can whatever. Not a lot of these. Not a lot of options on the mono, but if we'll have a look on the Flux, then we will see here a lot of others. So besides taking, can delay them, we can cache them, we can collect, concat, delay distinct. Just a second, hopefully going to the back pressure part to try to answer that question as well. So you see. Coming back to your question, I've mentioned that most of the details are on the code part. Whenever the actual back pressure support is implemented, these methods need to be used. On back pressure buffer, or drop, or error, or whatever we want to happen. So both buffering a series of messages and then telling to or sending to the publisher a message to slow down, or dropping them, or raising an error, or whatever might be needed. There's also pretty thorough error support, especially on the Flux publisher, and support for a lot of the reactive pipeline operations. We won't have a lot of time to do that. Let's quickly start the application and the debugger. Sure. You want to set a breakpoint anywhere, or? Okay, let's add a delay in here, perhaps. Delay elements, duration of, not of seconds, but of millis. Millis, so this will be the many. For now, let's, yep. I keep forgetting that the image is mirrored, so I tend to look there. So we'll host the localhost many. Just a second. For some reason, this starts in a 2. Okay. Started. So one other aspect to note in here, by just bootstrapping the Spring Boot webflux, sorry. The Spring Boot starter webflux, we have the Netty web server automatically included. So whenever we start our application, we just have Netty started on port 8080. And going back to the controller, I've just added an element delaying in here so that we can see them. So let's see, first of all, the first one. Yeah, sorry, forgot the product. Yep. So we have a simple product, which is returned in a reactive mode, but since it's a single one, we don't have a lot of benefit. Let's see many. It takes some time because I've added a delay in there, but they will be pretty soon returned. Just a second, or several seconds actually. Yep. So because I've added those that delay in there, a lot of products are returned, but with a slight delay. If we want to, do you want to see anything specific, or? You won't necessarily like the feeling because the stack traces are pretty complex, and we will get into the internals of the project reactor library, but we could try. Let's see it again. Yep, so we are in So as I was saying, a lot of calls. So until here we have Netty, reactor Netty, IO Netty, and so on channel, and then from there on we come into the reactor core, and from there everything is reactor core, and a little bit on top it's a little bit of Spring Framework and our own controller. So a lot of the internals of as I was pretty much sure that it will be. Let's see something. This will further take some time. The key point from here on, in my opinion, the most useful aspect is the usage of those reactive pipelines, meaning the definition and the handling of those messages in a reactive mode and also in a non-blocking mode. So everything from here It's mainly in the project reactor and the operations that we want to perform. Sorry, deleting this one, returned. There's also a possibility to return an event stream from presentation endpoint. This publisher of products or a flux of products will not stop because it's an infinite stream. So it will just publish things forever. We can also try that. Stream. So this will not end. If we leave it like this, it will stay forever. I'll close this because we don't want to wait that long. Sure. Yep.
On the first one.
Yep.
On the first example, when you put the delay, shouldn't they come one by one?
No, they all come together. They come in a single a single batch.
Isn't that blocking?
The delaying of elements, as far as I know, the answer is the same. It depends. It depends on the reactive pipeline. For some of the calls, yes, it might be blocking. But for some calls, for example, for parallel processing, for parallel processing pipelines, it doesn't necessarily, or I presume at one point it might be blocking. This is a good question. If I would have the, no. Yep. I agree. Once again, I think it depends on the use cases. If we want to see some, I don't know, thinking of an example besides testing, delaying elements.
Yeah. Okay. So my question was, the last one with text event stream value.
Yep.
I saw the benefit of it because you could see the responses came one by one. And I was expecting on the other one, where he put the delay of 300 milliseconds, to also see them one by one. But instead it was blocking, and we only saw the result at the end. And for me, that was blocking. There was no asynchronous there, or non-blocking event. And I see it just as a normal REST call.
In this example, yes.
I think the reason is because it has this produces type text event stream value. This is
Yeah, I think he's right. The main difference is the producing, the type of response produced.
But what's the benefit? This is what we were wondering.
Sorry?
What is the benefit of the first one, of the many?
The benefit of this one, or which one?
The one with the many.
The benefit in this very simple example, I don't think there is any. But think about this publisher not on the presentation layer, but somewhere deep below. So somewhere on the business logic layer or on the data access layer, where we want to do a throttling on the returned responses. So I think on that layer we can have several benefits, because we can add those delays on the produced elements either in a synchronous or in a parallel mode. So I think it always depends on the use case. Think about doing several processing stages, and those stages can be in parallel, and each of those returned elements, besides coming in a lot of elements, thousands of elements maybe, just delaying a few of them before serving them to a subscriber from the top. So I think it depends on the use case. I definitely understand your question. I'm trying to think of a use case when on the business logic or on the data access layer. I think it depends on the business logic.
Maybe some kind of circuit breaker? Like a hystrix, like it breaks your circuits after a lot of number of calls, or it delays them programmatically if there are too many.
I don't think they have thought about them in that manner, so delaying them. I will also want to read their documentation to see exactly or some specific use cases. Based on what I've read so far, they are mostly useful, or they might be useful on the data access or on the business logic layer. So this is, I think it depends. Once again, totally understood. On the presentation layer, no. On the data access layer, it depends. On testing, once again, I think it can be useful. So think about it, an example. If we wouldn't delay them, we might have a stream of, I don't know, 1,000 or 1 million entities or responses from a database. And we would want to process them. We might want to throttle them, to delay them a little bit. And to do that in an either synchronous or parallel mode. Does it make partial sense? Yep. And not only on the client, but also on the application logic, on the business logic. Yeah, the client, think about the client might not even see that. So in this example, the browser was the client. But in another use case, this code might be further down, and the browser might not, or the client might not see anything from that code. That client would just see that it got a response, several orders, for example, back, and that's it. It doesn't know what was in the back. We can further elaborate that. Yep, please.
One last question, guys.
The media type event stream.
Yep.
From what browser on is that supported?
The media type is from Spring 5 and from Spring Boot 2.
Okay. And from the browser, because you call it from Chrome?
Yep. The browser...
It understands the
yep.
event
It
stream?
understands the content type, because I'm sure you know it returns a different content type.
Okay. Thank you.
Thank you. Thank you also. My last slide was not this one, sorry, this one. So in case anyone might be interested, we are offering, meaning our group of trainers, we are offering a 2 days long reactive programming training, which is much more in depth than what we discussed. So it goes over more in depth on the reactive programming and using reactive programming with SQL and NoSQL databases, Kafka, Spring Cloud, and a lot of exercises. So this is just a teaser for that one. And absolutely the last slide. Yeah.
Thank you, Bogdan.
Welcome.